Are we alone in the universe? It's one of the biggest, most profound questions we've ever asked. And for centuries, it was just speculation, a question for philosophers. But not anymore. Today, it's a full-on cosmic detective story, a real investigation with real data. So let's dive into the hunt. Just look at this number. Since 1995, the number of confirmed planets we've found outside our own solar system has just exploded. We're talking over 6,000 confirmed worlds, and that's just the tip of the iceberg. Scientists estimate there are billions, maybe even trillions more in our galaxy alone. So it's not a question of if other worlds exist. The real question is,
Are any of them home? And that is the central mystery, isn't it? With all these countless worlds out there, could just one of them have the right ingredients, the right conditions for life to get started? This is the question that drives this entire incredible quest.
so here's our game plan for this explainer. We're going to follow the case files step by step. First, we'll look at this galaxy of worlds we've uncovered. Then, we'll open up the Planet Hunter's toolkit. After that, we'll see how scientists narrow down the suspects with the Goldilocks zone, search for chemical fingerprints of life, and finally, take a peek at the next frontier in this amazing hunt. We're living in what's truly a golden age for this kind of science. The search for other worlds has officially moved out of the realm of science fiction and into a real data-driven field of study. We're not just guessing anymore. We're gathering hard evidence about planets that are light years away. But here's the number one challenge, and it's a big one. We can't just go there. The distances are just mind-bogglingly vast. So astronomers have to be cosmic detectives, working a case from trillions of miles away. They're looking for the faintest of clues, tiny pieces of evidence carried across the galaxy on beams of light. Okay, so how do you even find a planet in the first place? How do you spot a tiny, dark world orbiting a brilliant, blazing star? Well, you need a pretty clever toolkit. Let's take a look at the primary methods we use to identify our initial list of suspects. By far, the most successful technique is called the transit method. This is the bread and butter for telescopes like Kepler and TESS, and it's actually beautifully simple. You just stare at a star, and you wait. If a planet's orbit is lined up just right, it will pass in front of its star from our point of view. When it does, the star's light dims, just a tiny, tiny bit. By measuring that dip, we can figure out the planet's size and how long it takes to go around its star. Pretty cool, right? Now, this is where it gets really smart. The transit method gives us a planet's size, but there's another technique, the radial velocity method, that measures how a planet's gravity makes its star wobble back and forth. That wobble tells us the planet's mass. And here's the magic. When you combine size and mass, you get density. And that's how we can tell a dense, rocky world like Earth from a big, fluffy gas giant. And let me tell you, these tools are finding some absolutely incredible places. We've got systems like TRAPPIST-1, which has not one, but 7 Earth-sized planets. And we're constantly finding other fascinating worlds orbiting stars really close to us. These are the prime candidates, the ones astronomers are lining up to investigate further. Okay, so we found thousands of planets. That's a huge list of suspects. How on earth do we narrow it down? Well, the first big filter is all about one thing: location, location, location. We start by looking for planets in what we call the Goldilocks zone. You've probably heard of this, right? It's that sweet spot around a star. Not so close that all the water boils away, and not so far that it all freezes solid. It's the region where conditions are just right for liquid water to potentially exist on a planet's surface. And since all life as we know it needs liquid water, this is our number one starting point. But, and this is a really important but, just being in the right neighborhood doesn't guarantee a nice place to live. A planet could be in the Goldilocks zone and still be a barren rock with no atmosphere, or a gas giant with no surface at all. So location gets a planet on the short list, but it is definitely not the final piece of the puzzle. This is where the real deep dive forensic work begins. To get closer to an answer, we have to do something amazing. We have to analyze the air of a planet dozens or hundreds of light years away. We're searching for the chemical fingerprints that could only be left behind by life itself. And that fingerprint has a scientific name, a biosignature. Now, to be clear, we're not talking about looking for radio signals or city lights. We're looking for something much more fundamental. a chemical imbalance in a planet's atmosphere that just shouldn't be there, unless something, some kind of biology, is constantly producing it.
So what would a smoking gun look like? Well, take Earth's atmosphere. We have lots of oxygen and a little bit of methane. Chemically, those two gases should not coexist. They react and destroy each other. The only reason they're both here is that life, from plants to microbes, is constantly pumping them out. Finding that specific combo on another world would be, wow, incredibly compelling. Same goes for gases like nitrous oxide, or something called dimethyl sulfide. And guess what? We are already doing this. The James Webb Space Telescope is an absolute game changer. It can stare at the light from a distant star as it filters through a planet's atmosphere. Different molecules in the air block specific colors of light, leaving behind a sort of chemical barcode. And using this technique, JWST have already found things like methane and carbon dioxide on an exoplanet called K2-18b, and even a controversial hint of dimethyl sulfide, a gas that, here on Earth, is only produced by life.
But, okay, this is the moment where we have to put on our scientist hats and be extremely cautious. How can we be sure? Could it be a false positive? Is it possible that some weird, non-biological process, some strange geology or chemical reaction we haven't thought of, is mimicking the signature of life?
And this is why context is absolutely everything. Before making what would be the biggest announcement in human history, scientists have to be the most rigorous detectives imaginable. They have to methodically rule out every single non-biological or abiotic process that could possibly create that same signal. It's about building a case so strong that, in the end, life is the only explanation left standing.
And what's so thrilling is that all this incredible science we're doing right now, it's really just the beginning. The next generation of tools is already being built, and they're going to push this cosmic investigation into a whole new era. So here's the roadmap for what's coming. Soon we'll have the Plato mission, which will be an expert at finding true Earth twins around stars just like our sun. Then comes Ariel, which will study the atmospheres of hundreds of exoplanets, giving us a massive sample size to work with. And then the big one. In the 2040s, the plan is for a habitable worlds observatory, a telescope so powerful it could directly take a picture of a planet like Earth and scan its air for those telltale signs of life. So, where does all this leave us? Well, we are standing on a threshold. Each new telescope, each new clue from a distant atmosphere gets us one step closer. We are slowly but surely ruling things out, narrowing the search. We're moving from a universe of pure possibility to one of actual scientific probability. And as this investigation continues, you have to wonder, what happens when we find it? What changes the day we know for sure we are not alone? We might just find out sooner than any of us think.